In this video we're going to talk about velocity versus time graphs, and we'll probably get to position versus time and acceleration versus time in another video. So let's look at the following problem. We have a particle moving in a along the x-axis. So its path is given by this blue curve, and its position at various times is shown by red dots. So initially it starts right here, and at time equals 0, and then at time equals 1 we've moved to the right to x equals 3, and then at t equals 2 we turn the particle turns around and it starts going in the negative x direction. So at t equals 3 seconds we're at 2, and then at t equals 4 we're over here at x equals -1. Now this is a very simple problem with a particle moving along a line in one dimension, and what we're going to do is we're going to plot this in the following way. So you can see I've already set this up. Now for time equals 0, that's this dot right here. And so I've listed I've replotted the red dots on this curve for the times indicated in the figure above. So what we can do is we can plot this. Now I'm not going to connect the dots with straight lines. What I'm going to do is I'm just going to draw a curve to fit all of these dots, just like this. There. So that's our position versus time graph. Now what can we do with this? Well, we can get a lot of information from this graph. So what I'm going to do is I'm just going to copy this, and we're going to plot it again on another page here. Alright, so let's go to a new page and we'll paste it in. For some reason this is going really slow. There we go. So there is our graph. Okay. Now, in a previous video we talked about average velocity. So if you recall, the average velocity is given by a change in position over a change in time, or the displacement over a time interval. Now let's label a few of these points. Let's label this point over here A. So at t equals 0, that's point A, and at t equals 3 we'll label that B. So let's find the average velocity over the interval from t equals, well, we can go in the interval from 0 to 3. So delta x is going to be our change in position. So it's our final position minus our initial position. And from the graph you can read the final position is at B, so that's 2 meters, and our initial position is where we started, which is 1 meter. So we get 2 meters minus 1 meter, and that's equal to 1 meter. And delta t is our final time minus our initial time, and that final time is 3 seconds, and we subtract 0 seconds, so that's 3. So we can compute the average velocity as delta x over delta t, which is 1 over 3 which is about 0.33 meters per second. Let me just put in units here. So that's our average velocity. Now let's look at the graph for a second. From the graph, we can actually look at what this represents geometrically. So let's draw a line. I'm going to connect point A to point B. And in fact, what I'm going to do is I'm going to draw this triangle right here. Okay. So this is, well, it doesn't look like, well, I drew that last line a little bit crazy. Let's redraw it. Okay. So there's a right angle triangle. And let's label a few of these sides. So let's look at the horizontal side here, this side right here. That side that I'm pointing to is actually the change in time. So we can label that delta t, and that is 3 seconds. And the vertical side right here, that's our change in position. So let's label that. So this side right there is delta, x. And if you look at what the average velocity is just delta x over delta t. That's actually the slope of the hypotenuse of this triangle. So we can label that as well, the slope of this line there is our average velocity. And remember, this is average velocity, not average speed. Right. Okay, so let's look at this another way. Let's say we make the time interval even smaller. So what I'm going to do is we're going to add another page here. I'm going to paste that same figure into our document. Okay, so now instead of, let's look at two adjacent times. So let's consider now this to be point A over here, and this to be point B. Maybe I should use different letters. Let's call this C and D. Okay, so we have, let's do the same thing we did before. Let's draw a triangle, a right angle triangle. It's going really slowly for some reason. Okay, well, while that is drawing itself, let's talk about what we're going to do. We're going to actually compute the average velocity over that time interval. So let's again write out V average is equal to delta x over delta t, and I lost that triangle somehow. There it is. Okay, so there's our triangle. Delta x is that vertical length, and our horizontal length is delta t. And our average velocity is just, in this case, going to be, well, the delta x is just going to be 2 meters. And our change in time is 1 second, so we have 2 meters per second. So over this smaller time interval, our average speed is actually larger than it was over the larger interval. And you can see, actually, there's an error here. The change in position is actually -2. Sorry about that. Remember, delta x is our final position minus our initial position, and our final position is 2 meters and our initial position is 4 meters. So the difference is minus 2 meters. So our average velocity is actually minus 2 meters per second. Now, we can also make the time interval even smaller, and we can consider something called the instantaneous velocity. So let's add another picture here. Any minute, there we go. Okay, so let's figure out the instantaneous velocity, so how fast this particle is going right at the point time equals 3 seconds, so this red dot right here. And the way we do this is by drawing what's called a tangent line. So a tangent line, at least locally, only intersects the graph at the point, I didn't draw this very well, at one point. So it's only going to, well, it doesn't, well, alright. So anyways, there is our graph, our tangent line. I'm just going to draw a triangle to represent it. I didn't do that very well. Let's try again. There we go. Okay, so, and the slope of this tangent line, so let's just label the tangent line. So this hypotenuse right here is our tangent, and the slope of the tangent line is the what we call the instantaneous velocity. Okay, so we call that V, and it's whatever that slope is. So in this case, well, I should have used a better triangle, but anyways, we want to calculate this delta x and this delta t, and maybe we can estimate. So our final position is this point here, and I'm going to estimate that to be about negative 0.8. So delta x over delta t, our final position, I just said was minus 0.8, and our initial position up here is about 3.5, so minus 3.5, and these are in meters, and our time interval, so that's about 4.2, our final time, and our initial time is about 2.6. So we get 4.2 minus 2.6. Now, how do I do this in my head? So I get negative 4.3 over 4.2 minus 2.6 is 1.6. And, well, that will be our slope in meters per second. Okay, we can actually calculate the actual values of that ratio. So let me just find my calculator. And what did I say it was? It's negative 4.3 over 1.6 is equal to negative 2.69. Okay, let's go back here. So this is negative 2.69 meters per second. So at that instant, at t equals 3, our particle, our instantaneous velocity is negative 2.69 meters per second. So that's how we can find the instantaneous velocity. Alright, I hope this was helpful, and I think I mislabeled what we were going to talk about. We're not talking about velocity versus time graphs. We're talking here about position versus time graphs. So let's just change that to x. Okay, thank you very much.